Hi, I'm Antonio Sala, and in this video we are going to start with defining which is the problem that Bayesian optimization tries to solve and motivating it in comparison to, say, deterministic optimization. Optimization is at the core of contemporary engineering. We wish minimum energy consumption, maximum performance, maximum efficiency. So all engineering disciplines try to optimize something. But, we have kind of two ways of optimizing things. First, we may just have, find the minimum of x1 squared plus cosinus of this stuff. So, in that situation, computing this takes just microseconds in a computer, and also I can compute derivatives, Hessian, whatever, so I can quickly evaluate them, and this setup is what we would call deterministic optimization. But in other cases, I wish to optimize the click rate of some advertisement campaign. Or, I am in a mining exploration and I wish to find a cobalt deposit. In both cases, I need to make experiments with an uncertain outcome and with a lot of noise in the measurements. When sampling some rocks, maybe I'm just unlucky, and even in the middle of my rich cobalt deposit, I just sample a little bit of worthless sand. So, the thing is that in those latter two cases, I need to incorporate statistics in the game. So optimization under some statistic models is what we might call Bayesian optimization. Nevertheless, usually Bayesian optimization, that name is reserved for a particular way of doing things that we'll comment upon in sequel videos. Let us first review what deterministic optimization does and how it may be different to statistical optimization. Basically, all problems have a function whose arguments are usually called decision variables, and I wish to obtain its, say, minimum value. So depending on some assumptions I may make on the function f, we have some specialized optimization techniques, such as convex optimization if f is convex, linear programming if f is linear, quadratic programming if f is quadratic, or for any smooth function, I can do gradient descent, so that if I start testing here, I can obtain the gradient and simulate, let's say, the physics of a ball descending in here, maybe with some inertia or momentum, let's say, so that it ends up at this lower point of the valley. The problem of gradient descent is that if I started here, I would have ended in a local minimum instead of the global one. But okay, that's the things that happen in deterministic optimization. Sometimes, in order to avoid getting stuck in those local minima, I throw the dice in this starting point, or I repeat things many times, and then I have the directed random search options in deterministic optimization. So the goal of all this is ideally to find the optimum in a fast way. If I am training a neural network with 100 million parameters, I wish to obtain the optimum that classifies best some cat pictures, and I wish to get the optimal neural network tuning in 2 hours instead of 2 years. So I wish to be fast, and being fast means evaluating f few times if possible, but okay, if it takes microseconds, few, maybe just a few billion times. Or maybe I also wish to avoid calling this Jacobian and Hessian construction and usage not so many times. And in fact, in multivariable problems, if I have to optimize over 100 decision variables, I don't wish to invert 100 times 100 matrices with those Jacobian and Hessians if possible, because that may take long. But the issue of computing time and memory requirements and the issue of local versus global minima are the things that we deal with when choosing a suitable deterministic optimization technique for my problem at hand. But now, if we move to Bayesian optimization, what is that in a very vague sense? Well, I wish to carry out the same problem, optimizing a function, but my model of that function is a statistical one. What do I mean with a statistical model? Well, that needs further explanation. I mean, a deterministic model is this kind of expression, sinus, cosinus, sums, products, exponentials, so I can quickly evaluate it and its first, second, or fourth derivative if so wished. But my statistical models of a function will be, say that what I know about the function at a given point x, in this case R2, is just that it is a random variable with, say, a given mean, which can depend on x, of course, and a given variance or standard deviation. So my theoretical assumption on my function is that for each x I have a random variable. So in the Bayesian optimization case, I assume that I do not know the actual value of the function at a given point until I go and evaluate it. And the function can take a lot of different shapes. For instance, I may have a prior assumption that will be used for Bayesian inference, of course, prior, posterior, etc. And my prior may have a mean function so that my f of x, this is, 0.6 x squared minus 0.4 x, something like that, plus a given normal variable. In black I have this mean function, and that normal variable will be 0 mean if I extracted the mean outside, and its standard deviation, well, I can draw, let's say, a 95% confidence interval, so that I get that 95% of the samples, let's say, of my function should be in between these intervals. But this is a random function prior knowledge, let's say, and then my functions can be, let's say, any of those bluish realizations I make. But there is still something missing, in the sense that, I believe that these realizations may be similar to the actual function in the middle of this stuff that I wish to optimize, but perhaps I don't think that my actual function to being optimized has this shape. Then how can I tell my algorithms that that orange line is extremely unlikely or impossible? If you see, the 95% confidence interval still holds, but the thing is that if I know that the underlying function is smooth and continuous, let's say, for instance, then if I call this point A, and this is f of A, and I call this point B, this is f of B. Well, if the function is continuous, then f of B must tend to f of A if I moved B towards A. So these three bluish lines are random functions, but they are continuous. In fact, they are smooth, like infinitely differentiable. So how can I get randomness as well as these other calculus-related properties? Because, if f of A is a random variable, f of B is a random variable, then maybe f of A takes this value and f of B takes this value. But the thing is that if the function is continuous, then f of A must be close to f of B. If A and B are close, that's the idea, and that means that they are not statistically independent. Even if f of A is a normal of a given mean mu A and some sigma A, let's say, some variance sigma square, and f of B is a normal with a given mean mu B and sigma B squared. In order to ensure continuity, then mu B must tend to mu A when B tends to A. Sigma B must tend to sigma A and the correlation between these two random variables must tend to 1. If B tends to A, then they must be copies of one another. So if A is 1 and B is 1.000001, means must be practically coincident, variance must be practically coincident, and also correlation must be 0.9999999 or larger. So that is the missing bit in my description. It is mandatory to develop the concept of random function with what we'll call a covariance kernel, saying that the covariance between these two random variables is a function of the points, and in fact, in many cases it's just a function of the distance between the points, in order to formally encode this continuity stuff into the statistical framework. If distance tends to 0, covariance must equal variance, so correlation is 1. And correlation only will be allowed to decrease if distance increases, sort of. Of course, the details of that need a lot of theoretical justifications, in the sense that, well, that is called stochastic processes, the collections of random variables associated to an index variable. In this case, the abscissa is the index variable. I have one random variable for each point. In fact, I have an uncountably infinite number of random variables in here, but those random variables are not statistically independent. They have some non-zero covariance, and usually we would say that will depend, on the distance between the points. The larger the distance is, the lower the statistical correlation is allowed to be, and the statistical correlation must be 1 if distance tends to 0. So with this kind of concepts, covariance kernels and whatever, then we build the so-called statistical processes, and well, in most applications we use normal distribution because, the normal distribution is a very famous one that appears when we sum a lot of independent variables, and we have closed forms for posteriors, variance, covariance, confidence intervals and the like. So, assuming that I have a collection of random variables, each variable associated to one of these x, with some covariance between them given by a covariance kernel. If everything is normally distributed, then that's called a Gaussian stochastic process, and that's the fundamental tool in what the computer science community calls Bayesian optimization methods. If I had not Gaussian stuff, then maybe I would need to do some Monte Carlo trials, whatever, but I cannot do Monte Carlo trials in an infinite number of random variables, so things must be suitably resolved. And then the theory underlying that is the Gaussian process theory that is needed as the basic building block of Bayesian optimization. So for the moment being, we will end up our discussion by summarizing what we have said. In this video, we have discussed what is optimization, either from a deterministic point of view, in which I have just a function known and I can evaluate it and I can compute its first, second or 20th derivatives if so needed, and depending on the assumptions on it, I can get specific tools for the job so that they efficiently optimize it. And then we had an alternate way of looking at functions and their optimization, which was the Bayesian optimization. My model was a statistical model of the function with some mean function and variance function that allowed me to write, if I assume they were normal, let's say, some mean black plot and some confidence intervals. And the issue is that apart from saying that I have a random variable with some mean and variance, at each point I needed to encode some continuity and differentiability via some covariance kernel in order to force the statistical correlation to be 1 when b tends to a. The formalization of that under some Gaussian assumptions, it's called Gaussian stochastic process. There is a lot of theory under it, and those Gaussian processes are the basic building block of the so-called Bayesian optimization techniques that we will delve into in subsequent videos. For the moment being, we end here. Thanks for watching.